welcome back to our next session. What we discussed in previous class, the various dissolution models are there. In that, diffusion film theory are also called as stagnant layer theory. And next one is Danckwerts model. Okay. Now I'm going to discuss about Danckwerts model. What diffusion film layer theory said? There is a formation of stagnant layer at solid liquid interface, right? The dissolution is the rate limiting step. They said like that. Then the Nernst equation, Noyes-Whitney equation, and Hicksel-Croghan, these are the three types of equations which are clearly described the diffusion mechanism of the dissolution theory. Okay, then next model is Danckwerts model. What it says? Danckwerts did not approve the existence of stagnant layer and suggested that turbulence in the dissolution medium exists at solid liquid interface. Okay, once again you read it. Danckwerts did not approve the existence of stagnant layer. That means here no stagnant layer formation will be takes place. In case of diffusion layer or film theory, there is a formation of stagnant layer at SL interface, solid and liquid interface. And Danckwerts suggested that there is a creation of turbulence in the dissolution medium which exists at solid liquid interface. Instead of stagnant layer, here turbulence is there. Remember that stagnant layer is present in the diffusion layer or film model theory. In Danckwerts model, there is a presence of turbulence at solid liquid interface. And the Danckwerts model, see here in this picture, they clearly shown that this is the solid substances and the layer surrounded the solid drug substances is solid liquid interface. In that interface, it is having the concentration gradient at the interface is less than concentration of solution, right? So then here see some packets like shapes are observing in this picture. What it is? This is the fresh packet of solvent approaching the interface. The packets are denoting the solvent, and this in this packet, this black color packet is having some drug, and this without drug it is showing like some empty packet, and with drug it is showing some, there is a presence of some content, and this is the bulk of the solution. In the bulk of the solution, the concentration of bulk of the solution is more. The concentration of drug in the bulk of the solution is more, and in the liquid interface the concentration of drug is more. Okay, so after when drugs gets dissolved into this bulk of the solution, the sum of the drug will be engulfed this fresh packet of solvent. So there is a creation of turbulence, that is a bulk, that is turbulence will be created by formation of these packets of solvents, right? Are you clearly observed? Are you noticed what is the difference between Danckwerts as well as diffusion film layer theory? Here the formation of packets of solvents will be happened. The drug will be entered into the solvent packet in the bulk of the solution. At solid liquid interface, the concentration of the drug will be more than the solution, and in the bulk of the solution the concentration of drug will be less in the concentration of drug at interface. Okay, the Danckwerts model is expressed by the following equation, that is V into dc by dt is equals dm by dt is equals capital A into cs minus cb under the root of gamma into d. What is the gamma? Rate of surface renewal. Here there is renewing of your surface will be taken place. M is the mass of the solid. A is the area which is used for your which is area which is useful for dissolving the solid substance, and D is the diffusion coefficient, and CS is the concentration of the drug at interface, and concentration of the drug at bulk of the solution. Same thing, same abbreviations here also used as in case of diffusion model. You just refer for this, what is V, what is A, and I also told. Okay, V is the volume of the solvent, how much volume you have used here. So only the difference here, there is no stagnant layer. In the diffusion layer, there is a formation of stagnant layer. And one more important thing, here the creation of turbulence is there with the solvent packets. Okay, so there is a chance to get renovalized the surface of the solution every time. This is about Danckwerts model. And the last third one is interfacial barrier model or surface renewal theory. Okay, it is called interfacial barrier model. An intermediate concentration can exist at the interface as a result of solvation mechanism and is a function of solubility rather than diffusion. In this case, the drug molecule will undergo solvation process rather than a diffusion. It doesn't undergo diffusion mechanism. The intermediate concentration which is useful to get particular solubility, so saturation solubility, at that point it will attains equilibrium at solid as well as liquid interfaces. The concept is given by G is equals to Ki minus Cs minus Cb. G is the dissolution rate per unit area and Ki is the effective interfacial transport constant. Cs and Cb are the same as before, that is dissolution Danckwerts model as well as diffusion film theory. Okay, so here you have three different theories for drug dissolution. Apart from these three, Danckwerts model as well as diffusion film theory are very important. There is a scope or chance to ask in there your examination point of view. And what is the conclusion of these three dissolution theories? The diffusion layer model and Danckwerts model based on the rate determining step, right? That controls dissolution in the mass transport, and solution solid equilibrium is attained at SL interface. That SL interface is denoting that solid liquid interface. And finally, third one, that is interfacial barrier model, can be extended to both diffusion layer model as well as Danckwerts model. And then next important factor which affects your drug absorption. Okay, that is first point. What is this? Under physicochemical factors, first one we learned about drug solubility, right, and drug dissolution theories. And next factor is particle size and effective surface area of the drug. So you just think it, your particle size of drug will be less means definitely it is having more surface area. If it is having the large particle size, it is having less surface area. See ma'am, you just apply your mind, so listen carefully, then only you have adopt the subject. Okay, smaller the drug particle, greater the surface area. Your surface area can be classified into two types: absolute surface area and effective surface area. Smaller the drug particle, greater the surface area. Write it down. And surface area will be classified into two: absolute surface area and effective surface area. Absolute surface area is total surface area of the surface of particle, and effective means what? Area of solid surface exposed to dissolution medium, which is effective. It is effectively exposed to the dissolution medium. See clearly, absolute means total surface area of the solid particles. Absolute, total surface area of the solid particle. And effective surface area is area of solid surface. How much area of solid surface will get exposed to the dissolution medium? That is nothing but effectively. And then smaller the particle size by micronization, greater the effective surface area. More intimate contact between solid surface and aqueous solvent, higher the dissolution rate, increase in absorption efficiency. You all know that if your particles will be present in micron in size, definitely there will be a chance to get more absorption efficiency. And particle size reduction has been used to increase the absorption of large number of poorly water soluble drugs. And already you know the examples of drugs which are having poor water solubility: griseofulvine and nitrofurantoin, digoxin, tolbutamide, dishydroxycoumarin. These all are having poorly water soluble drugs. So how you can increase the solubility, or how you can increase the drug absorption in such drugs? You may decrease the particle size. There may be a chance to get more absorption of these types of poorly absorbed drugs or poorly soluble drugs. Griseofulvine has extremely low aqueous solubility, and material of normal particle size give rise to poor and erratic absorption. So micro-sized particles improve the absorption. That's what I am telling. But it is improved even more when it is formulated in ultra-micron size particles as a monomolecular dispersion in polyethylene glycol as a solvent for griseofulvine. If you will get, what is our main aim in to reach maximum absorption rate? So the poorly aqueous soluble drugs are having low absorption rate. So you can increase them. You can increase these poorly water soluble drugs absorption by decreasing the particle size. So, and one more important thing I forgot to tell you, whenever you are writing in your exam, so for each and every factor which is influencing your absorption, so you have to explain them with a drugs examples. Without drug examples, they are not considered for your paper evaluation also. So you have to write must and should for each drug, for each parameter, you have to write at least one or two drugs examples, right? Okay. Next, one more important point which affects your drug absorption physicochemically, that is polymorphism and amorphism. You already know what is polymorph, more than one form. Many compounds form crystals with different molecular arrangement. How can you say that? By knowing the structure. Polymorph, amorph. Okay, these polymers may have different physical properties such as dissolution rate or solubility. See, ma, here polymorphs are of two types: enantiotropic and monotropic. Enantiotropic example is sulfur, and monotropic polymorph example is glyceryl stearate. So 40% of all organic compounds exist in various polymorphic forms. Polymorph means more than one form. Okay, more than one form it exhibits. By knowing its structure, we can estimate that it is a polymorph. And 70% of barbiturates and sulfonamides exhibit polymorphism. And what do you mean by amorphism? These have greater aqueous solubility compared with your polymorph. Okay, because the crystallinity nature is very less. These have greater aqueous solubility than the crystalline forms, because the energy required to transfer a molecule from crystal lattice is greater than that required for non-crystalline solid. So in case of polymorphs, there are crystals. So you need some energy to break down the crystal. What is the use? Why should we need to break down the crystal? Because we will attain good solubility, good dissolution, good absorption. So for that reason, we need to achieve, means definitely we have to break down the crystal. In case of amorphous forms, there is no need of breaking your crystals. There is a less chance to form a crystals among the moiety, right? So, examples are amorphous form of novobiocin 10 times more soluble than crystalline form. Suppose your novobiocin is having two forms, amorphous as well as crystalline forms. So, amorphous form is 10 times more soluble than crystalline form because the crystals will be formed by the use of covalent bonds. Definitely, you require some external energy to break down the crystal or to enhance its dissolution or absorption or bioavailability. These three are the consequence processes which are underwent absorption, right? So how the absorption of these three states will be, which one is showing more, which one is showing less? Amorphous form of solid substances are having more absorption than metastable forms and then stable forms. So what we concluded after learning this polymorphism and amorphism, amorphous forms are showing better absorption because there is no chance to form a crystal lattice. Simple thing, simple thing. Okay, and next important factor, physicochemical factor which influences your absorption is hydrates or solvates. Okay, the stoichiometric type of adducts where the solvent molecule incorporated with the crystal lattice of solid. So here your drug moiety is having crystal lattice, right? So in that crystal lattice your aqueous solvent will be incorporated. So your crystal lattice will be incorporated with the aqueous solvent, that is called hydrates. So your drug compound first forms a crystal lattice and it is absorbs, it is incorporated into the aqueous medium. Then it leads to the formation of solvates. Trapped solvent is the solvent of crystallization. The solvates can exist in different crystalline forms. Solvent, it is having crystal as well as it is having solvent molecule, right? So there is a chance to get pseudopolymorphs and the phenomena is called pseudopolymorphs. So these are not completely polymorphs and these are not completely amorphous. So that's why the name called pseudo. It exhibits two type characteristics because the crystal lattice will be engulfing or incorporating solvent molecules. When the solvent is association with drug in water, the solvent is known as hydrate. Solvent is association with drug in water. The solvent is known as hydrate. In case of solvates, the aqueous medium is more. Your substance will be in the crystalline form. In case of hydrate, the solvent is association with drug is water. The solvent is known as hydrate. Okay, see here, anhydrous form of theophylline and amphiphylline. It is showing with high aqueous solubility, dissolve at a faster rate, more bioavailability than their monohydrate and trihydrate forms. Okay, theophylline and amphiphylline exhibit three types of forms: anhydrous forms, monohydrate forms, trihydrate forms. Your anhydrate form of theophylline is having so much of it is needing, the anhydrous form will need more aqueous solubility than monohydrates or trihydrate form. That's why more bioavailability will be observed in the case of trihydrate form and monohydrate form. So hydrates or solvates are also placed an important role to improve your drug solubility. Either furtherly it will be improved your absorption rate. So anhydrous form of theophylline and amphiphylline is having less solubility as compared with monohydrate and trihydrate forms. Okay, and next one more important form, that is salt form of the drug and how it will influences. The salt form of the drug will be influences particular pH. Okay, at given pH, the solubility of drug, whether it will be acidic or basic or in salt, or else it is may constant. So, at given pH, the solubility of the drug, whether acidic or basic or is salt, is a constant. While considering the salt form of the drug, pH of the diffusion layer is important, not the pH of the bulk of the solution. So, you may consider when you have gone through this dissolution or diffusion processes only the pH of the diffusion layer, not for the pH of the bulk. So you have to consider your diffusion layer pH, not the bulk of the solution. For salts of weak acids, how it is? For salts of weak bases, how it is? So H plus into D is less than H plus into B. That is diffusion layer hydronium ions. Bulk of the solution hydronium ions. For salts of weak acids, the hydronium ions are more at diffusion layer. Okay, the hydronium ions of bulk of the solution is less in case of salts of weak acids. For salts of weak bases, H plus ions, hydronium ions in the what is this diffusion layer is greater than hydronium ions which are present in the bulk of the solution. So weak acids is what it says, for salts of weak acids the hydronium ions at bulk of the solution is less. For salts of weak bases the hydronium ions of diffusion layer is more. So where hydronium ions at diffusion layer is equal to hydrogen ions of diffusion layer, and B is the bulk of the solution. So you understood some concept here, and we will discuss it in very clearly by observing the graph, this picture. This is the salt of weak acid. See ma, the diffusion layer of higher pH is 5 to 6. Then the bulk of the solution relatively pH is 1 to 3. This is the acidic condition, right? The salt of the weak acid, it will diffuse the solubilized particles into 2. See ma, these are the fine particles and this is the solubilized form of the drug, and this will enters into the systemic circulation, and these fine particles will undergo rapid dissolution. Then drug will enters into the systemic circulation, that is nothing but your plasma. Fine precipitated of weak acid. Whenever your drug will be available in the solution form, okay, your drug will be available in the fine particle form. The fine particle form of the drug will enters into the systemic circulation or plasma will be more rapid when it compared with your solubilized form of the drug. The graph is showing, the graph is observing this mechanism only. Okay, so then other approach to enhance the dissolution and absorption rate of certain drugs is by in situ salt formation. How? Okay, increasing in pH of microenvironment of drug by incorporating buffer agent. For examples of drugs are penicillin and aspirin, but sometimes more soluble salt form of drug may result in poor absorption. If your drug will be having more salt form, so definitely in some cases, not in all cases, it is having poor absorption. The examples are sodium salt of phenobarbital and phenobarbital. Tablet of salt of phenobarbital swelled. It did not get disintegrate, dissolved slowly and resulting in poor absorption. See how the clear picture is. The sodium salt of phenobarbital is having less absorption. Actually, what is our aim mainly? The drugs which are having salt form, they will get more absorption rate, right? But here the salt form of phenobarbital is very less absorption or poor absorption because the tablet is swelled, but it is not get disintegrated, but the tablet will not get disintegrated properly. Okay, so the graphs showing the variation SEMA, it all shows the dissolution profile versus salts. When you take the time on x-axis and take concentration on y-axis, the concentration is mg per ml. Okay, and it's showing the penicillin plasma concentration in fasting subjects after oral administration. See, it's showing the dissolution profiles. Among these all four forms, benzathine salt is having less absorption rate as potassium salt. See, here the concentration the concentration curve will be like this, and it is showing the plasma concentration in fasting subjects after oral administration. And finally what it is saying, apart from calcium salt, benzoyl salt is having less solubility. That's why I'm saying that some, even though they are in salt form, they are showing poor absorption. Okay, so amount of drugs that exists in the ionized form and unionized form. Okay, that will be discussed in next class, ma. Okay, till now what we discussed, what are the physicochemical factors which influences your absorption rate. The first foremost important point, that is solubility, drug solubility. In that we discussed about three different kinds of drug dissolution theories, right? And then in second one, what is the parameter? Salt form of the drug we discussed. Hydrates or solvents are also we discussed. Solubility and drug dissolution theories are also discussed. Okay, so these many factors you have. First you read thoroughly these 4-5 factors, then we will come to discussing about that pH, pK and all. Okay, then we will meet in the next class. Thank you.